Okay, so in the last 2-3 recordings we learned about diodes and especially semiconductor p-n junctions that we can use or we want to use as diodes. So as a quick reminder, ID for a semiconductor diode is given by this expression. And we saw that, if VD is much larger than NVT, then we can say the diode is on, and ID is approximately given by this expression, or equivalently VD is given by this expression. And if VD is much less than NVT, including negative values, particularly negative values, ID is almost zero, practically zero, right? And in this case we say the diode is off, and in this case it is on. On means that it is conducting current, off means that it is not conducting measurable current. It may be a little bit of current. So let's go through one quick example here to see how we actually solve a circuit with a real diode in it, right? So how do we figure out the IV in a real diode? So here's a circuit that we want to solve. I have a DC source of 5-volt DC source, a 2.5K resistor, and a diode. And the goal is to find, let's just say, this current, or let's say the voltage and current across the diode. Okay, now if I go back to my ideal diode circuit, I can see that in this circuit I expect the diode to be on, and I expect it to behave like a short circuit. In that case, I would go and quickly calculate my I and V, and I'll be done. In this case, I can probably still expect the diode to be on, but I cannot calculate the I and V that quickly anymore. It's not a short circuit anymore. It's a nonlinear device. So let me write my KVLs and KCLs. So KVL tells me that if I sum up these voltages in this loop, they should add up to 0. So V in, the 5 volt at the input, is equal to the current through the resistor is the same as the current through the diode, so 2.5K times ID plus VD. And we had a similar equation before. At that point of time we said, okay, so this is what KVL tells me, but I have two variables and one equation. I need another equation to relate ID and VD to each other for me. Now I have it, right? For a p-n junction, it looks like it should be on. I'm going to make an assumption. If you're not sure, start with an assumption of off. If it is off, then the current is 0 and VD will be equal to V in, which is 5 volts. If VD is 5 volts, it cannot be off. It is much larger than NVT, and it will start to conduct current. So the assumption of off is probably not a good one to start with here. We assume on, and it looks like it can be on. It looks like it can conduct the current. And if that's the case, I can go and plug the value for ID and VD from the equation. So I know that ID-VD relationship for the diode is this. Now, how do I solve this circuit? Now, because I know the diode is on, let me get rid of this one in this expression and either get rid of it here or just use this alternative equation. Okay, so I have two equations, one from this line and one from KVL, one from the device properties, one from KVL. The question is, how do I solve this? It's not a linear system of equations anymore that I could form the matrices and invert them and be happy and do everything quickly. It's a nonlinear equation. I still have either a log or an exponential function in there, which doesn't make it easy to, or doesn't let me use one of those techniques that I learned before to apply to this case. So how do I do that? Well, if you have a computer, they can solve it, right? So numerical methods, you can apply numerical methods to this equation and solve it. If you're sitting behind your calculator and you want to figure out what the value of the voltage and current are going to be, there are graphical methods that people used in the past, but now with calculators that can calculate, let's say, equations or formulas for you relatively quickly, things are easier. So what we do here is that we guess. We basically start from somewhere and check our assumption as we did before. And where do we start, and how good are we in choosing our steps and fixing our iterations is going to be the factor that determines how fast we converge to the final or the right answer. So let's just make an assumption for ID here. I'm going to use this equation, and I'll tell you why I do that. But I'm going to use this equation and this equation. So what I do is that I calculate some value or estimate, guess some value for ID, calculate VD from it, plug the values of ID and VD that I have into equation at the top, and then compare that to 5 volts that I have. So let's just call the right-hand side of this equation A. So let me see, I look at this circuit. It's a 5-volt power supply, 2.5K resistor. If the diode was ideal, I would have a short circuit over the, if I had a short circuit, then the current would be 5 divided by 2.5K. And I just realized that I'm pointing at something that you don't see at home, so sorry about that. So if the diode was ideal, this would be a short circuit. The current through the loop would be 2 milliamp. That's a good starting point. So let's just assume that the current is 2 milliamp. I already know that I'm overestimating it, right? Because the voltage drop across the diode is not 0. It's, let's say, something. We said it's normally between 0.5 and 0.7. So not all of that 5 volt at the input drop across the resistor. Something less than that will drop across the resistor. But this is some starting point that I can quickly calculate and use. And if ID is 2 milliamps, then I can calculate VD very quickly from it. I forgot to bring a calculator. So I'm going to run MATLAB here. You obviously don't have to do that. It's probably an overkill if you already have access to MATLAB. You may want to solve the exact equation. But with a regular calculator, you can do those kinds of calculations fairly quickly. Okay, so I'm just going to use MATLAB as a calculator here. For an initial value of 2 milliamp N of, let's say, we didn't talk about the values of N and IS. So for this value, let's assume that IS for this device is 1 nanoamp as you have it in your slides, and N is 2. Okay? So going back to MATLAB, I can calculate ID. ID is equal, sorry, VD. VD is equal to N, that's 2 times 0.025 for room temperature operation, times the log, that's natural log in MATLAB, of ID that I assumed, so 2 milliamps divided by IS of the device, which was 1 nanoamp. That's 1 to the minus 9. And I can calculate that. And then from that, I go and calculate the value for A. The parameter A that I had was 2.5K. So here is the process. I assume a value for ID. So I assume 2 milliamps, right? Then I go and do the calculation for VD based on that ID. And then I go and calculate A, the right side of the KVL, based on the values of ID and VD that I have found. And I run all of these. And what happens is that VD is going to be 0.72 and A is going to be 5.7. So I'm going to go back here. VD is going to be 0.72 and A, based on that calculation, is going to be 5.7. So I overestimated the value of my VD and ID, right? Because A has to be 5. I'm slightly above 5. I need to go back and fix that estimation. So the next guess that I may have can be, for example, 1 milliamp. Let's see what happens if I choose 1 milliamp. If I choose 1 milliamp as the new value for ID, and I go and calculate all of these again, now I have 0.69 volts for VD and 3.19 for A. So VD is 0.69 and A is 3.7 volts. Now it is less than 5, right? So I overestimated at the beginning. Now it looks like I'm underestimating it. The true answer should be somewhere in between, but probably closer to the first guess that I had. So I'm going to say 1.7 milliamps for my third guess. And again, I go back and redo my calculations. You normally do this with a calculator. So let's just choose 1.7 milliamps for ID and recalculate these values. And sorry, the previous one, this was 3.2 volts, or you can keep 2 digits. Now, with this current estimate for ID, I have VD of 0.717 and A of 4.96. So let me just take a note here, VD of 0.717 volts and A of 4.96 volts. This is close enough, right? So if, for most practical reasons, this is within 1% of the final value. The final value is 5, you're 4.94, you're within 1% of the final value. And I'll be happy with this answer. So this is the value that I take, and this is the current for ID. So the final answer is ID is 1.7 milliamps and VD is 0.717 volts. And as you can see, through these iterations, you may overestimate or underestimate the next step, and you have to go back and correct it based on the calculations. And you go through these as many steps as necessary. Usually, once you are within 5% of the final answer, you assume that's good enough accuracy for hand calculations. And if you need to have more accurate results, you usually resort to computer simulations. So that's that for doing diode calculations. And you have examples in your textbook, in your slides on how to go through on some examples, and then you can actually go through them and then exercise. So for example, the next slide is a circuit with two diodes in parallel, but one of the diodes is significantly larger than the other one. How do you calculate ID for each one of those two cases? And if you're solving that circuit, note that ID for the two circuits will be different because ISs are different, but they have the same VD. And that should help you write the KVLs relatively easily and solve that circuit. Now, with one circuit, with one diode in the circuit, things are not too bad. You can solve the circuit with a few iterations. If you do a little bit of practice at home, you should be able to get to the right answer within at most, let's say, 4 or 5 iterations, within, let's say 1-2% of the final value. And it needs a little bit of practice. It needs a little bit of, let's say, insight into these circuits and how big should the next step be. For example, over there we had 2 milliamp, 1 milliamp. The next one we could have chosen 1.5 milliamp, which is in the middle of those two. If it was a linear problem, that would probably be a good choice. But this is a nonlinear problem, and I probably would want to bring a little bit of that insight into my solutions as well. So maybe you can cut down on the number of iterations from 6 to 4 or 3. Nonetheless, this can become tedious very quickly. You should do a few of these on your own, but this calculation can become tedious very, very quickly. And we'd like to find ways to simplify the calculation of these diode circuits. Now, let's go back and have a look at the IV characteristic curve that we had for the diode. So, and again, we are not changing how we assign ID and VD in this course. So in a quiz, in an assignment, do not choose them arbitrarily, right? Stick to the convention, and you will be graded and then expected to do the work based on this convention. So if you look at the ID-VD characteristic curve for a PN junction diode, we saw that for all the negative voltages, we basically cannot measure anything. But for all the positive voltages, initially the currents are still very small. Remember that IS is so small that when multiplied by e to the 2 or e to the 3, nothing much happens. But once you have e to the 10 and e to the 20 and so on and so forth, you start to notice an exponential growth or actually some current. So 0 for the negative values, and all of a sudden it just shoots up. Or at least that's how we see it on a linear scale. Now, we can solve circuits based on this. We saw that it's not really, it takes a while. It takes time to solve circuits using that nonlinear model. So what we are going to do is that we are going to come up with a simplified model for this diode. So this is ID equals, or let me just use the other color. Okay? What we are going to do is that in order to solve these diode circuits more quickly, we already know that if you use an ideal diode model, it's not really too difficult to solve those circuits, right? So you just replace it with the short circuit or open circuit. You usually have a linear circuit left that you know how to solve and analyze quickly. With a PN junction there, it's not that easy. So what we want to do is that we want to find a way to solve these circuits with PN junctions in them somehow similar to what we did with ideal diodes. Now, as we said before, we noticed that the IV characteristic curve for a PN junction is similar to an ideal diode characteristic curve that is shifted to the right. If I look at an ideal diode characteristic curve, the orange curve here, it looks like that, a PN junction is resembling that, with the exception of the little bit of curvature at the bottom here, is resembling that. But it's shifted to the right a bit. By how much? By this value, VD on. So it looks like that, once you turn on the diode, the voltage doesn't change by much from that point onwards. We call that VD on. And for typical diodes, VD on is in the range of 0.7 to 0.8 volts. 0.7 for large power devices, 0.4, 0.7 for large power devices, silicon-based, and 0.8 for integrated ones. For the ones that you buy from a component supplier, a discrete diode like the 1M4000 series or similar devices, VD on is a good value to start is about 0.7 volts. For most discrete devices, this is a good, safe assumption for VD on. 0.6, 0.7 is usually where they are. So you assume that much value for VD on, and you treat the PN junction as an ideal diode whose characteristic curve is shifted to the right by VD on. In other words, what you're going to do is that you're going to take this diode and say, when I'm solving my circuits, I'm going to assume that I have an ideal diode, which is a short circuit when it is on and an open circuit when it is off. So this is ideal. But this ideal diode has its properties shifted to the right a little bit. So I'm going to put a voltage source in series with this guy to represent that shift. This voltage source value is VD on. And each diode that I have in my circuit I'm going to replace it with this combination. So this goes and sits in your circuit wherever you have a diode. You just take that diode out and put this combination in and then solve the circuit as before. So this represents a semiconductor PN junction. So in this case, we are ignoring the small changes in VD as you change ID. So we're assuming that VD is more or less constant. So for that reason, we call this the constant voltage drop model. Meaning that when the diode is on, you assume that there is a constant voltage drop across the diode, as we said, normally about 0.7 volts. And that voltage doesn't change much. So constant voltage drop model, or for short, constant voltage model, right? And by doing that, we simplify our calculations significantly. Now, again, if you go and figure out if that diode is on or off, in most cases you're left with a linear circuit, linear system of equations that you can solve in one shot. And basically life is going to be easy again. Now, let's see how we can use that model in a circuit. So here is an example. We want to find the input-output characteristic curve or relationship for this circuit. I have two resistors and the diode here at the bottom of that resistor. This is V out that I'm after, V in. And the goal is to find the characteristic curve. Basically, assume V in is changing from a very large negative value to a very large positive value, and plot that input-output relationship. This is my diode. VD is like this, and ID is in that direction. Now, I'm going to use the constant voltage model. And assume that VD on is something, let's say 0.7 volts. Well, if this was ideal, if the diode was ideal, I can use the experience that I have from previous examples and say, you know, for negative voltages, if the diode was ideal diode, right? If V in was negative, then what you would have is a current that wants to go from ground to your source. And if the diode is on, it's a short circuit, so the current wants to flow that way, but then that will be against the flow direction for your diode, so that is not going to happen. Then your diode, let's call it D1, off. If the diode is off, then you can actually quickly solve the circuit, take the diode out of that circuit, open circuit, there's no current through the resistors. You can easily show V out is equal to V in, right? No voltage drop across R1, therefore V out is equal to V in. And then if V in is larger than 0, then you can push the current from the source through R1 and R2 and diode to ground. Then your expectation is D1 is on, and therefore you can show that V out, you have a short circuit for that diode at the bottom. Therefore, you have a resistive voltage divider between R2 and R1. There is no voltage drop across the diode times V in. And the input-output characteristic curve would look like this. So V out is equal to V in for negative voltages, and then you have a breakpoint here where the slope changes. The slope here is R2 over R1 plus R2, and the slope here is 1. And when you're drawing these characteristic curves for your assignments or quizzes later on, those are the information that we need to see on that curve. We want to know where the breakpoint is, where the slope of that curve has changed, so it changes at 0, 0, right? And what are the slopes of those pieces of line before and after each one of those breakpoints? Now, something that should help you in analyzing these circuits is that the number of breakpoints in the characteristic curve is at most equal to the number of diodes. So if you have one diode in your circuit, assuming that you don't have any storage elements in your circuit, you should have no more than one breakpoint. So if you somehow figure out that there are 2 breakpoints in your characteristic curve, something has gone wrong. Now, if I go and apply the constant voltage model, or constant voltage drop model, we said, okay, we go and replace the diode with a combination of a diode and a series voltage source. So I will have my diode here, which is now an ideal diode, plus a series voltage source whose value is VD on. This whole thing represents my diode, right? So for each one of the diodes in my circuit, I put one of these combinations. VD on for the ideal diode internally, that's VD on from outside. This top to the bottom is VD1. And my interest is in finding V in, V out relationship for this circuit. In the interest of time, I'm going to leave this to you guys to solve at home, guys and gals. And what you will see is that well, again, for negative voltages, you don't expect conduction, right? So if V in is, let's say, minus 100 volts, I expect the current to flow from ground all the way to the voltage source, but the diode will not like it. And in this case, I actually have an ideal diode there. It will not let that happen. The current will be 0. And if the current is 0, then again, you replace the diode here with an open circuit. There's no current. There's no voltage drop across the resistor. And this is what you expect to see. So all the way for negative voltages, you can show that V in and V out are equal. However, in this case, for positive V in that are smaller than VD on, the diode is still off, right? So let's say if VD on is did we assume a value? VD on is 0.7 volts. So let's say if V in is 0.2 volts. So if V in is 0.2 and this is 0.7, for that kind of a voltage difference between V in and the voltage at the cathode of your diode, the current still has to go upwards. It still has to flow from the diode into V in, which again the diode will not allow, right? And therefore this curve actually extends to the positive values of V in. How far does it go? Well, as soon as V in becomes equal to VD on, then the direction of current can switch. So for anything larger than VD on, the direction of the current can switch, and now you have your new slope here. So R2 over R1 plus R2, and this is your breakpoint, whose value is VD on, and before that the slope was 1, so it's VD on and VD on, right? So it's just a breakpoint. It just changes the slope. There is no jump. And my recommendation to you is to just go on through the solutions. You know, start with a very large negative V in, write the equations for V out with the assumptions that you make for the diodes. Find that breakpoint as you increase V in. When does the diode situation change? And find the equation for V out after that breakpoint, and see if it matches this graph that I show you here. Through the live sessions, we can actually go through examples if needed. All right, so there's an example on the next slide where you have 3 diodes in series and you're asked to solve the problem using an ideal diode model, sorry, a PN junction diode model where the exponential relationship between the ID and VD basically makes the equations a little bit harder to solve. You need to solve it with iterations, versus the constant voltage drop model of, with the assumption that VD on is only 0.7 volts. Now, we have one more discussion to cover for today, and that is, what if we have circuits with multiple diodes, as we saw before. So in this case, I have this circuit, for example. There are 2 branches here, 2 diodes facing opposite directions. So this is one branch, bottom branch here with a voltage source. And a resistor value down here. So I'm assuming the 2 resistors are equal in value. Let's assume this is V bias or VB, let's just use VB. Name the 2 diodes, so D1 for the one on top, D2 for the one on the bottom. This is VD2, this is VD1, this is ID1 flowing in this direction obviously, and this is ID2 flowing in that direction. Okay, and the question asks you to plot VD-ID relationship for this circuit. And okay, with the PN junction, if you had PN junctions and you wanted to use the nonlinear equations, this cannot be done by hand. You know, you really have to spend a lot of time, or you have to be really, really good at what you're doing in order to figure out, you know, where are the breakpoints and focus around those breakpoints, and then other than those, basically assume a constant voltage drop or a open circuit and solve the circuit. Normally what helps is that you assume an ideal diode without any voltage drop across them to figure out what should be your assumption for the initial condition of the diodes and take it from there. Like what we did for the devices, for the circuits with an ideal diode in them. So in this case, I'm going to do the same. I'm going to make an assumption for D1 and D2 when, let's say, V in is under my control at a very large negative voltage, and then start to increase V in slowly and see what happens to the situation of those diodes. At the very beginning, for the very first step, I'm making an assumption. I don't know if my assumption is correct or not. So after I solve the circuit, I need to check my assumption. Once my assumption checks out, once I know that the assumption I made is correct, I go through the rest of the solution by increasing V in. But if my assumption was wrong, I need to go back and fix it before proceeding with the rest of the problem. So the very first step, you make an assumption, you verify the assumption. If it is not correct, you go and make another assumption, verify it until you have the right assumption after your assumption checks out, and then you go and start increasing the input voltage. So let's assume that V in is a large negative value. If that's the case in this circuit, my assumption is going to be that D1, well, I'll give you a second. What do you think is going to be the operating region for D1 and D2 in terms of D1 and D2 being on or off? So if you ask me, if V in is minus 100 volts, D1 cannot be off. It's a very large negative voltage here. It looks like the current should be able to flow this way. So my expectation will be that D1 is on. And for a large negative voltage, D2 likely cannot be on, because again, if the current needs to flow this way, D2 will not like it, will block it. So D2 off. Okay? So this is my initial assumption. I need to check it later. With that assumption, the circuit reduces to this. I'm using the constant voltage model. D1 is now only represented by a diode. Well, let me put the short circuit for the turned on diode here. So this is VD on, and I have the resistor here. For D2, I still have that voltage source and resistor and all that, but it's an open circuit now, right? So this is D2 and VB and R here. Okay, so the bottom branch, this is D2, this is D1, and this is my assumption. This is the circuit. Easily I can solve this using voltage division. What I notice is that the voltage, the bottom branch, because there's an open circuit in it, it's out of the, I don't really have to worry about it. And at the top branch, I notice the voltage here is V in plus VD on. Okay? And then V out is a voltage division between two equal resistors. So quickly I can see that V out is R over R plus R times V in plus VD on, or half of that value. Okay? Now, if that's the case, I need to check my assumption. Is D1 on and D2 off? Well, to see if D1 is on, I need to calculate ID1. Right? To check if the diode is on, you calculate the current. If the current is positive, the diode is on. So ID1 is going to be V out in this circuit here. ID1 is going to be this current. Right? So if you look at the voltages here, ID1 is going to be minus V in plus VD on over 2R. Right? The two resistors are in series, minus VD plus VD on plus V in over 2R. Now, is this a positive or negative value? Well, it is a positive value because we are assuming that V in is a very large negative voltage here, right? And this is larger than 0. Therefore, D1 is on. Right, so for minus 100 volts, VD on is 0.6, 0.7 volts. For minus 100 volts, that value is positive. So D1 is on. What about D2? Well, I assume D2 is off. To make sure D2 is off, I need to calculate VD2 and show that it is less than VD on, or I look at the ideal diode here, I calculate the voltage drop across that ideal diode, and I say it should be less than 0. So I look at the whole thing or just the ideal diode in that equivalent model. And if I do that, I can show that VD2 is equal to, I'm going to include the diode, basically I'm going to look at the voltage drop from terminal to terminal, right? So from this end to this end. So VD2 is equal to V in minus the voltage at this node is V out plus VB, whatever this VB was. Okay? And therefore it is V in minus 1/2 V in plus VD on minus VB. Right? So it is basically half V in minus half VD on minus VB. So is this positive or negative? Again, remember that I'm assuming V in is a very large negative voltage. So minus 100, if you put it in there, this is going to be less than 0. For definitely, it's less than VD on. And therefore, D2 is off. Okay? And from this point onwards, I know my assumption was correct. My assumption is checking out. I go and solve the circuit. So the next thing I do is that I go and find out when either D1 or D2 will switch. Well, between these two, I have the conditions for their operation. So I need to see where either ID1 goes to a negative value or 0, or VD2 becomes positive. So let's check ID1. So ID1 becomes 0 when? When V in plus VD on from this equation here, right? From this equation here becomes 0. So ID1, when ID1 becomes 0, the first diode turns off, so D1 turns off when V in is equal to minus VD on. Okay, so as I increase V in, if I hit VD on, minus VD on, D1 will turn off. But actually D2 can turn on before that. So let me check VD2. When does VD2 become larger than VD on? Because I need at least VD on to turn on that diode. So again, in this case, I use this equation here to see when that happens. So VD2 set VD2 equal to VD on. From here you can see that half V in should be equal to, move VD on to the other side of the equation, 3/2 VD on plus VB. And remember, V in is a negative value, so with a, let's say, VB value of, I'm going to just use some value here, so let's say in here VB is 2 volts and VD on is 0.7 volts. With those values, I can see that, VD 2 doesn't become equal to VD on before I have about, so that's 2 and 1 times 2. So before V in is about 6 volts, right? So D1 will switch when V in is equal to minus VD on. D2 will switch when V in is equal to 3 VD on plus 2 VB. So it's about 2 VB, yeah, about 6.1 volts, right? So let me just write it down here. D2 turns on when V in is equal to 3 VD on 2.1 plus 4. So 6.1 volts. Okay, so recall that I'm increasing V in from a large negative value. One of these two things will happen first. Sometimes both can happen at the same time in some special circuits, but in this case, this one actually happens first. What that means is that as you increase the voltage from minus infinity, D2 will turn off first. D1 will turn off first. And in that case, you go from the circuit that you had in the above to this circuit. So this is your D2 now. D2 at the bottom, off. D1 at the top, off. And a series voltage source and the circuit here. So this is my breakpoint. Okay? After that breakpoint, I have this circuit, and it's easy to show that in this case, V out is 0. So for V in larger than minus VD on, remember, I'm increasing VD on from a very large negative voltage. For V in larger than minus VD on, V out is 0. My D1 has switched once. I think the next change that will happen here will be because of D2 switching its operating region. Remember, D2 is from here to here, VD2. So this is my D2 pointing this way. This is the direction of the current. For D1, it was the opposite. Right? Once a diode switches state in a linear circuit, as you monotonically increase the input voltage or decrease it, they usually do not switch anymore. Right? So as long as you do not have memory elements. So I need to figure out when D2 turns on. In this circuit, I can show that VD2 is equal to V in minus, again, the KVL that we had before, V out plus VB. But V out is consistently 0, and therefore it's just going to be from here. You can see that VD2 is V in minus VB. When does D2 turn on? D2 turns on when VD2 is equal to VD on. And therefore from here you can calculate V in has to be VB plus VD on. For the values that we have in the above, this is 2.7 volts. So at 2.7 volts for input voltage, D2 turns on. You have again a new circuit once more. The top branch, D1, is off. I'm going to assume that it stays off. It usually is the case. So this is for D2. I have a short circuit now, a VB here, VD on here, and a resistor here. And the top branch that was here, because I have an open circuit in there, I don't really have to worry too much about it. It doesn't contribute to my circuit operation. And in here, I can show that, V out simply is what? V in minus VD on minus VB, or V in minus 2.7 volts. Okay? So for voltages larger than this is our second breakpoint. So for V in larger than 2.7 volts, this is what we have. So the range here is going to be larger than VD on and V in. Now we can put the upper boundary here, V in less than 2.7, and then for anything larger, that's going to be the input-output relationship. If you plot V in versus V out, so you have one breakpoint at 2.7 volts, one breakpoint at minus 0.7 volts. It's 0 between these two, and the slope is 1 afterwards. And what was it before? This is my voltage for negative inputs. The slope is half before that, right? So this is 2.7 and 0, this breakpoint. And this breakpoint is minus 0.7 and 0. And this is my input-output characteristic curve for the diode. And again, there are multiple examples of this in your slides and in your textbook. So please make sure that you study a couple of them, solve at least 2 or 3 of these. These are very, very important problems. We are going to see a lot of these kinds of problems for the rest of the course. And as you can see in your slides, you can see what happens if you try to solve this simple circuit, just 2 diodes and 1 resistor. Numerically, even MATLAB can have a little bit of difficulty solving a circuit this simple, and there are circuit simulators can actually do a better job than that. So that's that for this recording, and for the next recording we are going to talk about applications of diodes, and especially their small signal behavior and their use in rectifiers for converting AC signals to DC signals. So until then.